Hello, this is Sylvia and welcome to my latest video. I'm going to go through the examples manual that I had developed for OpenSees, but what I've actually done is I've downloaded all those files, updated the new formats. Some of them had things that don't work anymore, so I've pretty much fixed up the tickle files, and then I've converted them all to OpenSeesPy. And so what I'm going to do is I'm going to go through each one of the examples, but it's going to be both in OpenSees Tickle and OpenSeesPy. So it's a really good way to either learn one or the other, but really have an understanding of both languages and how OpenSees works for both. I'm a big fan of Tickle and the wonderful things that I can do in operating and creating programs that do some processing and pre-processing with Tickle, just because it's to me, it's a much more expandable language. But then Python has some nice features of being able to use Jupyter notebooks, the fact that everybody else uses Python, as well as some simple features for plotting and graphing. Even though I am a big fan of OpenSees, TK for building UIs, but I have to admit it's a little bit of a pain to just plot things. And so being able to bring in matplotlib and all these other libraries for Python, it definitely makes an advantage for working with OpenSeesPy. So my take on it is, why not just do it in both languages so that I can take advantage of both? Interestingly, I think there's some place where you can actually write in both languages. So I want to get myself educated on both, keep moving on both so I can find out what works best for me. So back to what I want to do. So here we are at opensees.berkeley.edu. And this brings me to OpenSees. You go to the OpenSees wiki page and you go to user resources. And I like the getting started manual, which I wrote. And then if you go in the command manual, but also if you scroll down to examples. So in examples, there's a lot of other examples that people have built. I'm a big fan of the one I developed, even though it's encouraging you to go see the other examples manual. I really did put a lot of effort into building this example manual in a process that you build, and every time you iterate on it, you learn a little bit more. So it just doesn't dump you into the complete examples, but I just really wanted to go through the pedagogical process of going through one step at a time. So if you click here is the link to the manual. What you can see, the manual is split into two different parts. One is, of course, the introduction, then looking at the types of model that you're going to be building and the types of lateral loads and the type of simulation processes, or pretty much the process that outlines what you need to do. And then here's the different examples that really build up from example 1 all the way to example 8, which is going from a simple cantilever with just numbers all the way up to a variable geometry for a 3D frame. Then section 9, or example 9, talks about section modeling and analysis examples, pretty much scripts on how to do moment curvature and that kind of analyses. So I'm going to go forward, and these links here just really bring you back to what I'm going to scroll through. So this is very much an introduction to the example manual that we're going to be working on. Now, of course, what I like to do is I like to break up my input into the build the model and then the analysis components. So what's going to happen is there's going to be parts in the examples, especially in the later examples. Well, one script builds an elastic model, another script builds an inelastic model, and then you can use the same script or different build scripts on the same analysis script, whether it's for running the gravity load, which I actually combine with the model, but whether you have an earthquake load or a pushover load. So that's broken up into two parts because you could do a pushover on an elastic type of system or on an inelastic system. So why rewrite the files or rewrite the script? It's always easier to just break it up into different parts. And you'll see that that's what I do here. Not only that, but even for some parameters, we make separate files. But I'm really trying to walk you through and getting to that point. I didn't want to just jump to that kind of an example. So the models that we're going to be looking at are 3 different types of models. One is elastic elements, using the elastic beam column element. I wanted to do this just because even though in the long run I would always use a section with an elastic cross section, so still a nonlinear beam column element, but I wanted to just kind of minimize the number of input parameters. So we got the elastic beam column element, and then we've got the force-based beam column element, which is a distributed plasticity type of element. When you have a distributed plasticity element, now you can define different cross-sections along the length. You can define elastic cross-sections, but you can also define inelastic cross-sections, and that's what I'm going to be focusing on here. There's 2 types of inelastic cross-sections. One is a uniaxial section, and one is a fiber section. So the uniaxial fibers, and I'm not going to say one is better than the other. They completely serve different purposes. Uniaxial section is an uncoupled, inelastic, uncoupled axial flexural stiffnesses and shears, and you do this at the section level and they're completely uncoupled from each other. It could be elastic, it could be inelastic. Sometimes you'll do elastic flexure or elastic shear or elastic axial for sure, and then you've got inelastic components for the others. So as you can see, when would you use that, or when would you use the fiber section? A fiber section, on the other hand, actually discretizes these sections so that you can have more PM interaction and PMM interaction. Loading, you have coupled behavior in the 2 directions. Well, sometimes that's great, but sometimes it limits what you're trying to do. And oftentimes, especially when you're doing analyses of buildings or systems like that, a fiber section can be computationally expensive and not even accurate. Oftentimes, you can use a phenomenological moment rotation relationship in a uniaxial section that's going to give you a more accurate representation of what is actually going on in the system, because you don't just have moment and shear response, but you can bring in additional bar slip or maybe additional flexibility due to the connection or the bolted connections. So phenomenological models, I think, are more complete than fiber sections. So my recommendation would be use a fiber section where you need it, where you need to model PM interaction. Now, axial force can be taken into account in how it affects the moment strength. I mean, you can define different cross sections and properties depending on whether it's a bottom column that has a lot of gravity load or if it's a top column that isn't carrying as much weight. What really matters in a fiber section is the variation of axial load during your time series or your analysis. If the variation is not significant enough, then you don't need to go to that. So you would use it in columns, especially outer columns, because then your quarter columns could also take into account the relationship or the interaction between bending in 2 directions. So there's going to be very few cases where you need the fiber section. Most of the other cases, you're going to want to use uniaxial sections, because uniaxial sections can be a lot less computationally expensive, easier to define, even though sometimes it's just easier to just, define the actual geometry. But they're also computationally less expensive. So I would carry the 2 and understand both models. So if we look at the 2 different types of elements that we're looking at, and then I'm going to look at the 2 different types of sections that we're looking at. And within that, what we really want to do is look at the uniaxial material, because even though it's called a uniaxial material in OpenSees, what it really means is just defining a force deformation relationship. So it could be a moment rotation relationship. It could be a moment curvature relationship. It does not have to just be representing a stress and strain. So maybe we should call a uniaxial model command. So I've opened up these tabs, and so let's look at the different options that we have for the models. So we've got the elastic beam column element, which is just element, which is really the command. This is the type of element you're using. The node, the element tag, and then node I to node J. Then if you have in 2D, you only have to define the A, the E, and the I, the bending properties and axial properties in the 2D direction. Now, as you can see here, there are no properties for shear, because the shear is just based on E and A, and it just doesn't even account for it probably. In 3D, now we're bringing in EA or AE. Drives me nuts, this backwards. I think E should always just go first. But anyways, AE, G and J, and then the bending about the two axes. Now this transformation tag belongs to the transformation that you've defined ahead of time, and we'll talk about transformations as we go through the examples. Pretty much it says it's a way, especially in 3D, to define what the local z-axis is. Very important. Here you don't need to because there's really only one z-axis. And the transformation command mainly handles also any sort of geometric nonlinearities. So this would also be flagging the p delta. And that's why you have it even in 2D. You can give a mass density. I've never put in mass density into the beam or column element. I pretty much just define it at the nose. I'm never quite sure. This is nice if you have different elements and different lengths, but if I didn't have the power of being able to program my input, maybe I would take it into account. Otherwise, it's just easier to deal with masses by assigning them at the nodes. And then here's a switch as to whether you want to do a consistent mass matrix or just go with the default of the lump mass matrix. Again, I keep my masses out of my element definitions, especially if I want to then switch over to a different type of element, then I'd have to define my masses anyways. So when we define an elastic beam column element, we never have to define any relationship or behavior for the cross section outside because it's all defined within the element. If you go to your force beam column element, which of course has 1.5 million options, my favorite is really looking at the integration types that are available for that, and it's got a whole lot of recorders. This is the old command, and I would set it aside here. I like this new command, the new format, and also I have to update the format of this beam column element. Here is pretty much what the input for this element type is. So what you need to do is you define the element and the node, element tag and the nodes and the transformation. And then right here, you input information about the integration type. What you could do is you use the old-fashioned Gauss-Lobato integration. That's what I believe I kept in the examples manual, because going into the integration just becomes a project on its own to try to understand the different integration procedures. It's awesome. As I said, there's a document here. There it is. Integration types can really take you for a ride on where you want to put your integration points and your weights. So at this point, maybe what I'd recommend is to just go with the original command that assumes a Gauss-Lobato integration model, where you say from node I to node J, number of integration points, section tag. So here I have one cross section at all points along my element. Now you can change this when you switch over to different integration schemes. And again, this is a little bit outside of the scope of what I'm trying to do here, but that's a great sequel to this video. And again, mass and these additional properties that I just leave out, especially if you're trying to work through an examples manual. Each one of these can become a dissertation. So in the beam column element, in the nonlinear beam column element, we have to assign a section, which means in this section you have to define it ahead of time before the element. Well, as I've said already, there's two types of sections. There's a uniaxial section and there's a fiber section. In the uniaxial section, you just say uniaxial, give it the tag, which is what we're going to refer to later, and then here's a little material tag which says which force deformation response that you defined before in a material is going to be applied here, and is this an axial force, moment, or shear or torsion type of quantity. And so then that gets assigned to the beam column element. Well, wait a minute, how do we define all three together in one cross section for an element? Well, that brings a different type of cross section, and I'm going to add that afterwards because you still also need it for the fiber section. In the fiber section, you give it a tag and a stiffness. Even though these are optional, there's some versions of OpenSees that force you to put this input. So if you get an error, make sure you define GJ. And then in a fiber section, we can define individual fibers. You can define patches of fibers or layers of fibers. So you can have individual fibers, give it a location in an area. You can define either a circular or rectangular patch. So this is great for concrete or any sort of materials. And then even layers of individual fibers along a line. So this is great when you're defining reinforcing. Now, reinforcing steel, you could do it in a linear line or even in an arc. So it's very handy to define cross sections to make things easier rather than having to define one fiber at a time. For all these fibers, they all need a material tag. So this is almost pretty much, I don't know if there's a figure here. I guess we need a fiber section figure, but I think this is the best representation. So each one of these fibers needs a material behavior to it, right? Is it concrete? Is it steel? Well, that's when you go to the uniaxial material, and there's a myriad of different materials because you could be doing a concrete fiber or a steel fiber. The other type of fiber of section that I wanted to bring in that's going to be coming in is the aggregator section. So the aggregator section, which is right here, what it does is it combines maybe a shear force response with a fiber section to put together one fiber section or one section that brings in, and it doesn't couple things, but it just assigns a axial force response that you define ahead of time, a bending moment response. So it really depends on, maybe these could even, if these are all elastic or inelastic, you can define a bunch of uniaxial materials and then put them together into this aggregator, defining the axial response, the shear, and the bending moment in torsion. So it's a great way. This would be the section that you actually put into your element. So that's pretty much it for the different types of sections. So let me see the specifics of what we're going to look into. So in the elastic beam column, you have elastic uncoupled axial and flexural stiffnesses. Sometimes you don't have to define shear. It's kind of taken as rigid in your element. Then the uniaxial section is going to be inelastic uncoupled axial and flexural stiffnesses, and you define all of them at the section level, which is using the uniaxial section command. And so what this user is going to specify is the axial stiffness and the section moment curvature characteristics via the OpenSees uniaxial command. In a fiber section, it's a little bit complicated. So it's not just more work in the input also, it's a more work for the computer. But now you break down the section into fibers where the uniaxial materials are defined independently. And I'm going to scroll it down to here to kind of show you what a fiber section looks like. So this is what a fiber section would look like. You define these patches themselves and the individual fibers. So the user specified the stress-strain characteristics via the OpenSees uniaxial command, uniaxial material command for all number of materials. For every material, you need to define a material properties, of course, and then you can define the section geometry via patches and layers in the fiber section. Two section geometries are going to be presented. One is for an RC rectangular section, and one is for a standard AICW section. What's really cool about this is with Tickle and even with Python is you can define a function, and that's what we're going to do, where the input, the user is going to, it's almost like an additional OpenSees command, where the user now gives you the number of bars and the geometry, and then your little procedure is going to actually go in and define all the different components of your uniaxial or your fiber section. So it may be a little bit of work the first time you do it, but then you can either inherit scripts, you can start from the scripting manual here, so you're never really starting from scratch. The kind of loads that we're going to be looking at are all going to be lateral loads as well as gravity, but gravity is included with the models themselves. So that I'm not going to highlight that one because every model type is going to have gravity. We're not building anything on the moon. So we're going to have two different types of lateral loads. We're going to have static pushover loads, and we're going to have time-dependent dynamic loads. In the pushover loads, the control node is located at the highest floor. So here's a rendition. If you have a single degree of freedom system, it's only going to have one node anyways. But just for generalization purposes. And then I'm going to have loads distributed, along the height that are proportional to the mass distribution along the height of the building. So trying to do a realistic pushover analysis. It's going to be two kinds. One is a monotonic pushover, and then it's in one direction, displacement control static lateral load. And then I'm also going to do so here's your pushover, and on the other hand, we're also going to do something cyclic. It's kind of a nice way of testing your model to see what the response is in all directions. So we're going to do a reverse cyclic pushover when one directional displacement control static lateral loading is applied, and the displacement cycles are imposed in positive and negative direction, okay? So we're going to push and pull all the way to the opposite direction. So it's a really good place. It's a script that's there that's going to make it a lot easier for you in the future. You just can modify the script. This is what a lot of people do. It's nice. I get a lot of questions oftentimes, and they're using, one of these original example scripts. Time-dependent dynamic loads that we're going to look at are going to be 5 different kinds. We're going to look at the uniform sine wave acceleration input. This is a great way to do a dynamic analysis without needing a ground motion, because it's hard enough to then figure out what the dynamics or how to even read your ground motion. So using a sine or a trigonometric function as your input is just a great way of doing some dynamic analysis. We're going to be looking at uniform excitation, so the same ground motion for all the support nodes, and then we're going to look at multiple support excitation using a sine function. And if you go back to past lessons, in a uniform excitation you impose accelerations, in a multiple support excitation you impose displacements. This is really just based on the formulation. Therefore, remember in your input and output whether you're getting absolute or relative accelerations. So a uniform sine wave is going to have sine wave acceleration input. Same acceleration is input at all nodes, restrained in specified directions. In a multiple support sine wave excitation, you're going to have a sine wave displacement input. And we're going to have different displacements are specified at particular nodes in a specified direction. So this is going to be all in the same direction anyways, but it's a great way of demonstrating what to do. I'm probably going to use the same input file for all of these, but you can actually impose different ones. And that's why you would use multiple support excitation. If these were all the same, then you would just go to the uniform. I'm going to do exactly the same thing, but now this is going to be earthquake input excitation. So uniform earthquake and a multiple support excitation for displacement. So I don't know if I just use the acceleration input and pretend it's displacement, or actually manage to find displacement histories. So here you would need to use the displacement trace from your ground motion. And then also demonstration on how to manage bidirectional earthquake loading. So different inputs are specified in 2 directions. Here I've got the tool, the horizontal and the vertical direction. And because it's a uniform excitation, it's going to be the same acceleration input for all of them. Remember, you can then, by looking at these individual cases, you can then figure out how to do multiple support excitation in multiple directions. So again, the objective here is to really just get you started. So what is a simulation process? Well, you're going to build a model. So you give the model dimensions and degrees of freedom. And this is what I follow in all of the examples. Then you define the nodal coordinates and the nodal constraints, which are the boundary conditions. Next step is you define the nodal masses. I like to do that even though I have a static, because especially the nodal masses, I'm going to use them to figure out what my loads are going to be in my load pattern for the static pushover. So it's still important even though it's a static analysis. Then you're going to do the elements and element connectivity with their transformation and materials and sections, depending on what kind of elements you're using. And then we're also going to be looking at sample examples of recorders for output. Again, these are very basic examples to just show you how things grow and really where to get started. In the next step, once you've defined your model, you define and you apply your gravity load. Remember to define your recorders before you apply gravity so that you're recording what's going on even during the gravity load. It's important because if you don't have convergence during your gravity load, there's something going on with your model. So that's always the very first step. So we're going to define nodal and or element loads. We're going to define the parameters for your static analysis. In OpenSees, you have to define all these parameters. It's not so hard, and most of the time, most parameters always work for most cases. You're going to analyze it, You're going to hold gravity load constant. You have to tell OpenSees to do that. And then we're going to reset the time to 0. The next step is going to be looking at the lateral load, those lateral loads that are defined above. So first you have to define the load pattern. The nodal loads for the static analysis and the support ground motions for the earthquake. Then you're going to define the parameters for your analysis. Tolerances, displacements, time increment. They're very different from your static analysis parameters. Then you perform your, for the static lateral load analysis. Oh, and you have displacement control versus time control, as well as load control, which really are all the same process, but it just really depends on what it is that you're checking. In a dynamic lateral load analysis, you can define the input motions and all associated parameters, such as scaling and the input type. You're going to define the analysis duration and the time increment, and then you're going to define damping, very important for these cases, and then you're going to need to send the command analyze. And then there's additional scripts on what to do if you don't have convergence. You can have this script on what to do if you don't have convergence during your gravity analysis, and it's a great time to check if you don't converge in your gravity analysis, there's something going on.